Welcome. Thanks for joining us today. We're going to be talking about analyzing distributed traces to find performance bottlenecks in your system. I'm Bryan Zimmerman, Product Manager with Google Cloud.
And I'm Francis. I work on distributed tracing at Shopify, and I'm also a maintainer of OpenTelemetry Ruby.
In order to speak about performance troubleshooting, first let's talk about performance problems. These are problems with the latency or compute utilization of your services. And these are things that will impact your users' experience of your product and your bottom line. These are often difficult because there is no clear error or event that has caused the issue. Instead, they may be an optimization that has existed in your system for a while, or there could be a problem that has creeped up or is otherwise buried.
Performance problems in large distributed systems can be surprising, and causality is often missing or buried in other telemetry signals. A couple of real examples we found with distributed tracing at Shopify. An RPC was executed twice unintentionally due to a quirk in the network architecture. And a value in Memcache that grew in size without anyone noticing and then suddenly became popular during a flash sale, exhausting network link capacity. Both of these jumped out really quickly from trace data.
Today, we're going to be highlighting a couple key tools from the Cloud Observability toolset. First is Cloud Trace. This is a distributed tracing tool that is particularly useful for latency scenarios, but it's also useful in any scenario where a downstream service is affecting upstream behavior. Then there's Cloud Profiler. This is a continuous profiling application that helps you find exactly what part of your code is responsible for an issue. These exist as part of a larger toolset. This toolset is based off the same planet-scale platform that powers Google's internal observability, so you know it's been battle tested. In addition, it comes with zero-day configuration out of the box for key Google services. So, for those who aren't familiar, let's talk about what distributed tracing is. Here's an example application architecture. Your users may communicate with the front end through load balancers. That will communicate in turn to multiple backends, including databases. However, today, your application is more likely to look like this. Many small microservices working together for a common goal. This is a great application architecture, but becomes very difficult to troubleshoot. Distributed tracing allows you to understand exactly how the request has moved through this environment, which definitely simplifies troubleshooting scenarios.
At Shopify, we're often known for our devotion to our core monolith. In reality, though, there's an increasingly large set of services orbiting that monolith, and performance is impacted by all services involved in processing a request, including third-party services. Distributed tracing provides visibility into the performance of these increasingly deep distributed systems that is almost impossible to achieve any other way.
Next, let's review continuous profiling. Continuous profiling helps specifically with what happens in a particular service. The intent is to identify the method or section of code that is contributing to the issue or the source of the optimization. Cloud Profiler takes profiles of your application at every function call in a sampled way. This means it's perfectly safe to run in production. These profiles are laid out on a flame graph where it's visually extremely easy to understand how these functions play together and where the cause of an issue is. When we talk to customers, the troubleshooting process typically follows these steps. You start with an issue and refine that issue as much as possible using the metrics you have. Then you try to identify the service that's responsible. This is particularly important for distributed systems. Further refining to the method or part of your code where the issue exists is extremely important for efficient troubleshooting. And then finally, looking at deep information such as logs and debugging tools help you come up with a viable hypothesis for what might be causing the issue. This is, of course, required before any resolution can be attempted, which needs to be pushed and confirmed using the same metrics that identified the problem for you.
In practice, we can treat traces as contextualized logs. Typically, trace instrumentation initially focuses on the edges in a service graph, where communication happens between services. Performance problems show up as large spans with large gaps between child spans, where we don't know what's going on. So the hypothesis part of our process involves incrementally filling in those empty spaces by adding instrumentation to our code until we gain some insight into what is different about this path.
Now let's see this in action using Google Cloud's observability suite of products. We're going to show you a series of demos on our demo application, Online Boutique. We'll take you from problem to service to method to hypothesis, starting with identifying and refining the problem. We're going to show how to use cloud monitoring to find and refine the problem you're attempting to investigate. As you can see here, we already have an incident related to latency. You can see from looking at the policy details that we've actually defined this alert to be 99th percentile latency sustained for 1 minute. This kind of alert configuration ensures that only real problems generate alerts and wake up our on-call tech. To understand the problem further, we're going to open up one of our pre-configured dashboards, in this case the performance dashboard. We can see a definite spike in latency in our server latency heat map. This can be shown both from the aggregate percentile lines as well as the distribution itself. Let's drill into the inflection point. At this point, we definitely understand what to investigate, which is gRPC server latency. Next, we're going to use distributed tracing to understand the source of that latency spike. With the problem well understood, it's time to identify the service where the issue most likely exists. To investigate the cause of this latency, we're going to use a new feature called example traces. This allows us to overlay sampled traces onto the latency heat map from within the monitoring dashboard. Here we can drill into the specific requests that generated those metric data points of interest. In this instance, it's quite obvious to see that most of the time is spent during the get product operation. We can check other requests to see if it's a similar pattern, and indeed it is. To validate our hypothesis, let's check some 50th percentile traces from before the spike. To investigate this further, we're going to open CloudTrace. Here we can further dig into the traces that exemplify this problem. This allows us to filter for additional details, including label values, and see the trend over time. As you can see, the visual representation of your entire request that Trace provides allows you to easily see where the problem is. In this case, as mentioned earlier, it seems to be in the product catalog service get product operation, which is done repeatedly and has been taking a much longer time than looking at traces from before the spike. Kaliana is going to show you how you can use Google Cloud Profiler to identify where in the code this issue or optimization can be found.
Now we will use Google Cloud Profiler to investigate which functions in your service code could be slowing it down. The default view of Profiler shows you a flame graph representation of your service profile. In this flame graph, we can get a bird's eye view of where your service is spending most of its time. Here we have selected the product catalog service, and we are specifically looking at the CPU time for the service. Just by looking at the flame graph, we can understand that most of the time is spent in this stack, which is the gRPC receiver for this service. Walking down the stack, we can see that parse catalog is where you're spending most of your time. Opening the top functions table and sorting by the total time, we can confirm that 68% of the total time is spent in parse catalog. Walking down the stack some more, we can see that this time is spent in actually a JSON unmarshalling function. So this should be the first focus of our optimization efforts.
To form a viable hypothesis, we're going to use logging and debugging tools included with Google Cloud Observability suite of products. We're going to jump to the related logs for this particular trace. In the previous demo, we found that the cause of the problem was most likely within the product catalog service. To dig into this further, we're going to filter to that particular Kubernetes resource pod. This can be done easily at the click of a button. And immediately, via the histogram, it's obvious that something has changed around the time of this issue. Let's jump to the start of this problem to see what's happening. And similar to what we saw within Profiler, this service is successfully parsing the product catalog very, very often and repeatedly, certainly more than it was previous to the issue starting. This confirms our hypothesis that the problem is related to parsing of the product catalog. To further dig into this, we can inspect the messages from our logs, correlate that with the behavior of our code via debugger and our IDE. Cloud Debugger allows you to inspect what's happening within your running application by injecting snapshots or log points whenever you like in your code. We'll show this in action by going to our currency service, and let's take a snapshot at line 155. And what we can see here on the right-hand side is instantly we're able to see details of the local variables at the time the snapshot was taken. Now, what if you only want to take that snapshot in certain circumstances? Maybe I'm chasing an issue with only a certain region or a certain user. Well, you can add conditions. These are written in the language of the code that you're debugging, or expressions, which will print certain aspects of your application as you write them. Now, maybe I don't want a snapshot that occurs once, but I want to, on a recurring basis, take a log point. Well, you can do that. You can inject log points that will be run every time the code is hit, not just once. And again, these can be written with any condition, written in the language of the code you're debugging, and with any message. The editor allows you to do this easily. You can write whatever log point you want, as long as it will not affect the running bytecode and it meets certain memory and CPU footprint requirements. These features allow you to understand what's happening within your actual production application. This can be a game changer when it comes to understanding and debugging issues that only happen on production. It also makes it much easier for operators, SREs, or developers to troubleshoot issues without having to wait for long deployment cycles. The demos you've just seen gives you a highly guided experience to troubleshoot performance problems using Google Cloud's Observability suite of products. But sometimes the answer is not that simple. There isn't a single request or even a set of logs that shows you exactly where the problem is. This is where understanding the system and its requests in aggregate is extremely important. In order to help with this, we've recently released a feature where traces can be exported to BigQuery. Any label that you send into your span data gets written as unique columns, which makes searching even easier. This allows you to use the power of BigQuery to perform custom analysis, and also allows you to retain data for much longer than the included 30 days. Now I'm going to hand things over to Francis, who's going to explain how this kind of aggregate analysis is done at Shopify.
At Shopify, we use BigQuery for aggregate trace analysis. I'm going to briefly demonstrate how we do that. Firstly, though, why do we need aggregate analysis? The typical approach to trace analysis is to search for interesting traces, perhaps by service and time frame, and either incrementally refine our search until we have a smallish set of traces to look at, or hope that the 1,000 or so traces returned are representative of what we're looking for and start clicking randomly. By viewing a few random traces, we're hoping that anything interesting we find is representative of a larger set of traces. Using a tool like BigQuery, however, we can analyze all the traces in a set and allow it to surface interesting information. We still often want to look at complete traces to provide more context, but we'll have confidence that the traces we look at will be truly representative. If we want to use BigQuery for trace analysis, we have to get the trace data into it somehow. There's a couple of ways you could do this. For example, at Shopify, we have a slightly complex ingestion pipeline using the OpenTelemetry collector, PubSub GCS, and batch upload to BigQuery. Google Cloud Trace provides a simpler option with trace exports. The schema that CloudTrace uses for trace data in BigQuery is determined by the Trace v2 API definition of span, so it stores one span per row with nested records for span attributes. Shopify's schema is similar, but based on the OpenTelemetry protocol definition of span instead. If we're performing in-depth analysis of something relatively constrained, our first step is always to extract the data we're interested in into its own table. This can drastically reduce query costs, leverage the query cache, and generally increase responsiveness. In this example, we're going to analyze synthetic load generated against a test shop. Almost all of the units of work performed by our core monolith, whether requests or background jobs, are scoped to a single shop, so we always tag request and job spans with the target shop ID. We know the time interval for the load test and the ID of the test shop. Our table is partitioned by start time, so we specify that as our first filter. We're doing a bunch of analysis that has no obvious partitioning or clustering characteristics, so we don't bother specifying clustering or partitioning for our destination table. We use a subquery to identify trace IDs that meet our requirements, and then copy all the spans from those traces to the new table. Here we've extracted about 8 gigabytes and 13.5 million spans from a 22 terabyte partition. This significantly reduces the working set for analysis. Let's start our analysis with some basic queries to figure out the services involved in red metrics. It doesn't get much simpler than this. This gives us a list of the services involved. Red metrics are a little more complicated. Let's focus on one service, the storefront renderer. We'll count requests per minute, filtering to the service and looking only at server spans. The key pieces here are truncating the start time, then grouping and ordering by the truncated start time. We can see around 45,000 RPM over the first half of the test, followed by a dip, and then an increase to around 175,000 RPM in the second half. I should note here that we're downsampling traces in the collectors, so we saw a significant multiple of this request rate, but this serves to show the general shape of the load. Note that we can trivially adjust this query to return a per second request rate. The BigQuery console is great for trying out queries, but once we start building queries like this, we want to easily visualize the results. There are many tools that integrate with BigQuery, including Google Sheets and Data Studio. At Shopify, we use Mode Analytics for data analysis. In Mode, we build our SQL queries separately, and then we can access the datasets by name in a notebook. Plotting our query results is pretty trivial. Here are the plots from our earlier queries, and from a similar query for request rate to our core monolith. To calculate duration as a distribution, we bucketize by minute and compute each percentile over each minute. We represent duration in microseconds, so here I'm converting to milliseconds. And here's what that looks like as a plot. Before we drill in further, one more high-level perspective we might like is the relationship between the services involved and the relative volume of traffic. This is variously called a service graph or service map. Here's what that looks like in this example. The key pieces we need to know are the source, destination, and request count for each edge in the graph. The query required for this is a little more complicated, but there's really two things going on here. The first part of this query considers requests that are represented by a single span. These are typically database or cache queries, where we only have instrumentation on the client side. The other set of requests we're interested in have two sides. So we grab the set of client spans with the trace and span IDs, and the set of server spans with the trace and parent span IDs, and then join them on the trace ID, where the parent span ID of the server is the client span ID. Grouping gives us the request count along each edge. So let's go deeper and break down request counts and durations by component. For request count, we query the Rails controller attribute as well, and group by both start time and the controller. In some cases, the attribute is missing, so we replace it with unknown. Plotting this gives us a request rate for the different controllers. Breaking down the duration by controller is slightly more gnarly. I built this query in the BigQuery console by trial and error, and a data analyst somewhere is probably having a fit watching me try to play one on TV. Regardless, our subquery extracts a start time, controller, and duration from the relevant spans, and then we compute the P95 partition by the start time and controller. The result is a little obscured by an outlier controller, which looks like the not found controller. We could ignore this controller in the SQL query, but it's easier to do it here with pandas. This produces a much clearer breakdown. Drill downs are also relatively easy with pandas. Here we've drilled down into the collections controller. We can then easily contrast the duration for this controller with the request rate for the controller from our earlier query. Now we might want to ask where we're spending time in aggregate in request to this controller. Let's start by querying all the operations performed during those requests. We have 26 operations, which is quite manageable. We have the expected Redis and MySQL queries and template parsing and rendering. Computing the workload contribution of each operation is as simple as summing the duration and grouping by the span name. Ordering by the cumulative duration allows us to quickly identify the heavy hitters. The top two aren't interesting, but the rest are leaf spans, and we can clearly see MySQL dominates, followed by Redis. We can further summarize by database type to see the cumulative MySQL and Redis times. In this service, we also tag spans with the time spent in garbage collection, which we can then extract and summarize. We're interested to know whether GC dominates any of the expensive operations. In fact, it doesn't. It accounts for less than 1% of time spent in MySQL spans and a little over 4% of overall request time. Alternatively, we can look at the contribution of different SQL queries. In this service, we tag MySQL query spans with a digest of the query template, which makes it easy for us to aggregate spans, and then we can search for examples and find the actual queries in another tag. Here we see one query clearly dominates. Finally, in the same way we did with controllers, we can analyze request rate and duration by arbitrary tags. This is a request count by zone. And this is a P95 duration by zone. We can see some small differences, but nothing especially exciting. If we instead look at cache hit versus miss performance, we can see a more distinct difference. And we can see that our cache hit rate is reasonable, at over 96%. I hope that's given you a taste of some of the types of analyses that you can perform over trace data using BigQuery. The key elements are getting trace data into BigQuery, which you can accomplish with Cloud Trace Export, then extracting interesting traces to a separate table, typically based on a time window. This helps to control query costs and greatly increases responsiveness. And finally, it's extremely helpful to have a tool to view the query results. At Shopify, we use Mode Analytics, but there are many other tools that integrate with BigQuery.
Thank you, Francis. And thank you all for joining. Please feel free to reach out for follow-up. And as always, visit us at cloud.google.com.